All right, so this is going to be our walkthrough for the homework assignment titled Differential Equations Test Review. The first few problems here will be calculator problems, and we'll move on to some non-calculator ones. So we've got this function, or not this function, but this differential equation, dy dx is equal to sine x over x. And the initial condition we've got is f of 1 is equal to 5. We want to find f of 2. Right, if f of x is the solution to that differential equation. And so we did quite a few of these in class where we weren't able to actually find an elementary antiderivative of our function, sine x over x. And so what we said was, well, then the integral of sine of t over t dt is just going to be a portion of our solution to this differential equation, right? And we know that if I had an x up here and some constant down here, and we could have some constant out here too, then the derivative of this function that we've written here would equal sine x over x, which is what we want. We also want the initial condition that f of 1 is equal to 5 to work as well. So I'm going to say this is f of x, but if I want f of 1 to equal 5, the only way to be able to evaluate this, right, at x equals 1 would be if this lower limit here was also equal to 1. And I can choose any value I want for that constant as long as it makes the equation still true. So I'm going to get rid of this c sub 1, and I'm going to call this 1 so that when I evaluate at x equals 1, this portion is equal to 0. Well, if I evaluate when that portion is equal to 0, then I need to add something to make it equal 5. Well, 0 plus 5 is going to equal 5. So what we'll do is we'll just get rid of this c sub 2, and we'll call this 5. And now we've got our function that satisfies the condition that f of 1 is 5 and that its derivative is sine x over x. So in order to figure out f of 2, right, f of 2 should just be the integral from 1 to 2 of our thing, sine t over t dt plus 5. Or you could write sine x over x dx plus 5 if you want. And that's going to be the pattern we'll use for all of these, right? The lower limit of our integral is always going to be that x value that we are given as our initial condition. And our constant out here is always going to be the y value. So we'll just do the integral from 1 to 2 of sine x over x dx and add 5 to it on our calculator. So we'll hit math. We'll go down to option 9. And we'll do our integral, as we said, from 1 to 2. And our function was sine of x divided by x dx. Make sure that your plus 5 goes outside the integral, not inside the integral, else you're going to get a very wrong answer. And we've got 5.659 here, if we round to 3 decimals. So for our next one here, we're going to use the same idea because this is another function that we can't actually take the antiderivative of, right? E to the negative x squared doesn't have an elementary antiderivative. So we're looking for f of 6, but first we need to find f of x, right? F of x is just going to be an integral of e to the negative t squared dt from some constant to x, and that constant is just going to come from this 3 here. And our constant out here will just be pi. That way, when I evaluate at x equals 3, the whole integral portion is 0, and we add pi to get pi. So we're looking for f of 6, so f of 6 should just be the integral from 3 to 6 of e to the negative x squared dx plus pi. If you still write it as t squared dt, that's fine. And we'll just use our calculator to evaluate this integral, and then add pi to it. So we've got math, and once again, just like the last one, we go down to option number 9. We're integrating from 3 to 6 of e to the negative x squared dx, and then we'll add to that our pi. And we get 3.14161223 or 3.142 if we round to the nearest thousand. All right, our next one here. We've got f of pi is what we're looking for, and f of x is the solution to dy dx equals 2 over ln x. And we know that f of 2 is equal to 3. We're going to do the same thing here. We're just going to say f of x is the integral from 2 to x of 2 over ln t dt plus 3, right? This 2 becomes this, and this 3 comes out here as our constant. That way, when we evaluate for f of 2, right, we have the integral from 2 to 2 of our integral that we can't actually evaluate, giving us just 0 since it's from 2 to 2. We add 3 to make the initial condition true. So now we want f of pi. F of pi should just be the integral from 2 to pi of 2 over ln x dx plus 3. So we'll use our calculator to figure out what that is. We'll hit math, option number 9, and we're going to go from 2 to pi, and it'll be 2 over the natural log of x dx. And we end up, oh, and I forgot to add our 3 to the end of that, so don't forget to add the 3. So plus 3 to that gives us 5.489. So those ones should all be pretty straightforward. Just use your calculator to approximate the integral and add that initial condition. All right, for our next one here, we've got a metal plate that's been heated to 50 degrees Celsius. And then it is placed in an oven that is set to 250 degrees Celsius and heats up to 100 degrees Celsius in 8 minutes. We want to know how much longer it will take to heat up to 200 degrees Celsius. So this is a Newton's law of cooling problem. Even though it's not cooling, it's heating up, right? So we're going to use Newton's law of cooling, which is T minus the surrounding temperature. So final temperature minus surrounding is initial minus surrounding times e to the negative kt normally. But since this is heating up, we're just going to use e to the kt. Right? So when it's heating up, we'll just use e to the kt. When it's cooling, we'll use e to the negative kt, right, for growth versus decay. So the first step here is to find the value of k using the given information. So it starts out at 50, and it increases to 100. So our final is 100, and our surrounding temperature was 250. So we have 100 minus 250 equals our initial of 50 minus 250 times e to the k times t, which was 8. It took 8 minutes for it to register that new temperature. So we end up with negative 150 equals negative 200 e to the 8k. And now we'll just solve for k. If you divide both sides by negative 200, you'll get 3/4 equals e to the 8k. If you take the natural log of both sides, you'll get the natural log of 3/4 is equal to 8k, or k is equal to the natural log of 3/4 divided by 8. And once we have that value for k, then we can figure out how much longer it will take to heat up to 200 degrees Celsius. So it's asking us how much longer, not how much time from the start. So now we'll use our new initial temperature of 100 degrees, because we want to know how much longer it takes from when it was 100 to get to 200. So we'll have our final temperature is 200 minus our surrounding temperature is 250 equals our new initial of 100 minus our surrounding of 250 times e to the kt, or we don't have t, that's what we're looking for, so it's t ln 3/4 divided by 8. We'll simplify a little. 200 minus the 250 gives us negative 50. And then we have a negative 150 e to the t ln 3/4 over 8. We'll divide by negative 150, just giving us 1/3 equals e to the t ln 3/4 over 8. We'll take the natural log of both sides, remembering that the natural log of 1/3 is the same as natural log 1 minus natural log 3, or just negative ln 3. And then on the other side, the e cancels out when we take the natural log, so we're just left with t natural log 3/4 over 8. And solving for t, we get t is equal to negative 8 ln 3 over ln 3/4. And we should be able to put that into our calculator to come up with an answer. So we'll do that. We've got negative 8 ln 3. And then we're going to divide that by the natural log of 3/4. And it should give us our final answer of 30.551 minutes later. All right, for our next one here, we've got a can of Coke that is at a temperature of 70 degrees Fahrenheit, and it's put into a freezer that's set at 20 degrees Fahrenheit. And after 20 minutes, the temperature is 40. And we know that the Coke will freeze at 30 degrees Fahrenheit, and at that temperature, the can is going to explode in the freezer. We want to know after how many more minutes will the can explode. So first off, we just have to find the K value, and note that this is a Newton's law of cooling problem, right? So we're going to use, just like in the last problem, the formula was the final temperature. So our final temperature that we had in our initial setup was 40, minus our surrounding temperature, which was 20, is equal to our initial temperature of 70 minus our surrounding temperature of 20, times e to the, this time it is going to be a negative K, because we're cooling, and then times t, it took 20 minutes for it to cool down to 40 degrees. So we'll use this setup to solve for K. So we have 20 equals 50 e to the negative 20K. And 20 divided by 50 is, of course, 2/5. We take the natural log of both sides, getting natural log of 2/5 equals negative 20K, or K is natural log of 2/5 divided by negative 20. And so we'll be able to use that to determine when this can explode. In other words, when is its temperature 30 degrees Fahrenheit? And we want to know how much longer it will take, after how many more minutes. So we're going to use, our final is 30, with our surrounding still 20. And our initial now is going to become this 40 degrees that we had already cooled it down to. So we'll have 40 minus 20, e to the negative kt. Well, since k has already got a negative sign in it, then negative k will just cancel out that negative sign, and we have a natural log 2/5 over 20 times t, where we're looking for t. So we'll just simplify down here. 30 minus 20 is 10, 40 minus 20 is 20, and we've got e to the natural log of 2/5 over 20 times t. We'll divide by the 2, giving us 1, or by the 20, giving us 1/2, is e to the natural log 2/5 over 20 t. Take the natural log of both sides. As we've talked about, natural log of 1/2, right, is natural log 1 minus natural log 2, or just, since natural log of 1 is 0, it's just the negative ln of 2. If we take the natural log of the right-hand side, the e to the power of, kind of the e goes away, right? So we just end up with ln of 2/5 over 20 times t. Or t is negative 20 ln 2 over the natural log of 2/5. So we'll just put that into our calculator and get an answer. Negative 20 ln 2. And we'll divide by the natural log of 2/5, giving us 15.129 more minutes. And that's our final answer there. All right, we got another law of cooling one here. We got a metal pan being removed from an oven, and it's placed on the counter in a room that's 70 degrees. And when it's removed, it has a temperature of 200 degrees. It takes 14 minutes for it to cool to 120. We want to know how much longer it will take to cool to 76. So again, we have to find the K value first using, just like the last two problems, Newton's law of cooling. And it is cooling this time, not heating up. So we have our final temperature, which in the initial setup is 120 degrees, minus our surrounding temperature of 70, needs to equal our initial temperature of 200 minus the surrounding of 70, e to the negative k times t, and it took 14 minutes to cool down. So 120 minus 70 is 50, and then 200 minus 70 is 130. We'll take the natural log of both sides after we divide by 130. So 50 over 130 is just 5/13. Now we'll take our natural log. And K is the natural log of 5/13 over negative 14. So we now want to know how much longer it takes to cool down to 76 degrees. So our new final is going to be 76. So we have 76 minus 70. And then it's again how much longer. So our new starting temperature is that 120 that it already cooled down to. So 120 minus 70 times e to the negative kt. And just like in the last problem, since the k value has a negative sign in it, the negative in front of our k that we're going to put in the exponent here can cancel out that negative. So we'll just have t times that positive version of the k value. So it's just t ln 5/13 over 14. And now we'll just solve. 76 minus 70 is 6, and this is 50. So we have 120 minus 70 is 50. 6 equals 50 e to the t ln 5/13 over 14. Divide by 50. 6 over 50 reduces to 3/25. And now we'll take the natural log of both sides. And solve for t. So t ought to be 14 natural log of 3/25 divided by the natural log of 5/13. And we'll go into our calculator and we will figure out what that is. 14 ln of 3/25. And we'll divide by the natural log of 5/13. And we get 31.066 more minutes. And that's our final answer for that one. For our next ones here, we're going to be looking at interest, also coming from separable differential equations here. So we have $3,000 that we're investing into an account that earns 2.36% interest. Compounded quarterly, we want to know how much money do we have after 3 years. So the formula is A equals P times 1 plus R over N, where R is the interest rate as a decimal, and N is the number of times we compound per year, all to the power of N times T. So our final amount should be our principal of 3,000 times 1 plus our interest rate of 0.0236 when we turn 2.36% into a decimal, right? We divide by 100, divided by the number of times compounded per year. And so if we're compounding quarterly, that's 4 times per year. And then up here we have 4 times the number of years, which is 3. So we're just going to put all of that into our calculator. So we've got 3,000 times, and it's 1 plus, I'm going to use alpha and then the button next to it for a nice little fraction here. If you don't have that option, just do parentheses for your fraction. Make sure that whole little fraction is in parentheses. Our interest rate was 0.0236. Our number of times compounded was 4. And we're going to raise that to the power of 4 times 3, which is just 12. And we end up with $3,219.43 when we round, as the problem said, to the nearest cent. $3,219.43. All right, for our next one here, we've got $2,000 in an account that's earning 1.55% interest, and we're compounding monthly. So same formula with 5 years this time. So we're going to have our final amount is going to equal our principal, our initial amount, times 1 plus our interest rate as a decimal, so 0.0155 when we divide 1.55 by 100. If we're compounding monthly, there's 12 months per year, so that'd be 12. And up here we have number of times compounded times number of years, 12 times 5. So really we just have an exponent up there of 60. So we'll go into our calculator here. We'll do 2,000 times 1 plus our interest rate of 0.0155 divided by our number of times compounded of 12, all to the power of 12 times 5, which is 60. And we end up with $2,161.06 when we round to the nearest cent. And that's our final answer for that one. All right, here's our last interest problem. We've got $400 that we put into an account that earns 3.24% interest, this time compounded continuously for 6 years. So this formula is a little different. It's A equals P, principal, times E to the interest rate as a decimal times T, A perp. Okay? So our final amount should be equal to our initial 400 times E to the interest rate in a decimal will be 0.0324 times 6 years. And so that's all we need to put into our calculator this time. We've got 400. We've got E to the power of 0.0324 times 6. And we end up with $485.83. And that's our final answer there for our last of these interest problems. So here we've got a half-life problem. We know that the half-life of iodine-131 is about 8 days. If we have a 40 milligram sample, we want to know how long does it take for that sample to now be 3 milligrams. In class, we proved that half-life, right, we'll call it T sub HL, is equal to the natural log of 2 over K. And we know that if the half-life then is 8, that tells us the K value for this problem. K should just be the natural log of 2 over 8. So we first need that, and then we'll just use our half-life formula. Y is equal to y naught e to the negative kt. Right? This is just an exponential decay formula. So y, our final amount is 3 milligrams. Our initial amount is 40 milligrams. We have e to the negative ln 2 over 8 times t. And we're just solving for t. So we'll divide by 40. We'll take the natural log of both sides. And we'll solve for t. So we end up with 8 ln 3/40 divided by negative ln of 2. And we can find out an approximate value for that. We'll use our calculator, 8 ln 3/40. And then we're going to divide that by the negative natural log of 2, which gives us 29.896 days if we round. All right, our next one here, we've got a new element here. We've got titanium 44. It's got a differential equation of dy dt equals negative 0.011002y, where t is measured in years. And it asks us a couple things. First, what's the half-life? And second, if a sample has 125 milligrams, when will it have 33 milligrams of weight? And so what we need to recognize here is that when we have the differential equation dy dt equals ky, that's an exponential growth or decay formula. If there's a negative in front of it, it's decay. And if there's not a negative in front of it, it's a growth formula. But this differential equation, that's kind of one of the whole points of these problems, is that the differential equation dy dt equals ky gives us exponential growth or decay when we solve it. So our k value here is just 0.011002. And our half-life is always equal to the natural log of 2 over that k value. And when we plug this into our formula eventually, which we're going to do in a second, right? When we plug this into our formula y equals y naught e to the negative kt, of course, we'll put in a negative 0.011002 because it's negative kt in that formula. But first, we need to at least approximate out what our half-life is. So it'll just be the natural log of 2 divided by that. We'll do that on our calculator. Natural log of 2 divided by 0.011002. And we get 63.002. I think our units here were years. So 63.002. Yeah, units were years. All right. 63.002 years is our half-life for titanium 44. Now, we want to know if a particular sample has a weight of 125 milligrams. In other words, if it starts at 125, when will it equal 33? Well, it's y equals y naught e to the negative k times t. And now we'll just solve for t. Dividing by 125. Taking the natural log of both sides. And dividing by negative 0.011002. And let's see what we get here on our calculator. natural log of 33 over 125. And then we'll divide by negative 0.011002 and get 121.051 years. All right, we got one more of these growth decay problems. This time we have the differential equation for plutonium-236 as dy dt equals negative 0.2425287y. Right? That being dy dt equals ky tells us it is exponential decay, right, with the negative in front of it. And so our half-life is going to equal the natural log of 2 divided by that k value of 0.2425287. So first we'll find that, natural log 2, and divided by, we had 0.2425287, which gives us 2.858 years. That's the first part of the question here. And then the second part says, we want a particular sample to decay to 22% of its original value. Well, that means that the final amount is 0.22 of the initial amount. So when we write out our formula here, we're going to have our final amount, or 0.22 y naught, is equal to our initial amount times e to the negative kt, or negative 0.2425287t. We can cancel out the y naughts, right, just by dividing both sides by y naught. It doesn't matter how much we actually started with. We just want 22% of what we started with. Then we'll take the natural log of both sides, giving us natural log of 0.22 is negative 0.2425287t, or t is the natural log of 0.22 divided by negative 0.2425287. And of course, we can put that into our calculator and see what we get. The natural log of 0.22, and we'll divide it by negative 0.2425287, and we end up with 6.243 years if we round to the nearest thousandth. And that's our final answer for that one. For the rest of the problems on this assignment, we're not going to use our calculator for them. So we've got pretty much just a bunch of differential equations that we're going to solve here. Starting off with a nice straightforward one. dy dx is equal to 3x squared minus 2x minus 1, with the initial condition that when x is 2, y is 3. So all we really have to do here is integrate and say y is equal to, well, the integral of 3x squared is x cubed. The integral of minus 2x is x squared. And a minus x plus some constant. And so what we need to do is find that constant by plugging in our initial condition that when y is 3, x is 2. Well, if we solve this, 2 cubed is 8 minus 4 minus 2. That's 8 minus 6 is 2. So we have 3 equals 2 plus c, or our constant is 1. So our answer should be y equals x cubed minus x squared minus x plus 1. And it asks for the interval of validity, which means we have to check for any discontinuities. Well, this is a polynomial function. It has no discontinuities, so this is valid for all real numbers, negative infinity to infinity. All right, for our next one here, we're just going to do the same thing. Once again, we're just going to take the integral of cosine 2x. Now, it requires a u sub, but I hope by this point we are to the point where we can just integrate cosine 2x really easily, right? Just in our heads. Right? We know the integral of cosine u is just sine u, so right. So it's going to be sine 2x, but then that 2 that's inside ends up giving us a 1/2 on the outside, right? Because if you do the substitution where u is 2x, du is 2 dx, and you'd have to put in a 2 and then a 1/2, right? So that's what gives us the 1/2 sine 2x. And of course, don't forget that we have a plus c there. Now we'll solve for our constant by plugging in 3 for y and pi over 4 for x. And so 2 times pi over 4 is going to be pi over 2. The sine of pi over 2 we know is 1. So we have 3 equals 1/2 plus our constant, or our constant is 5/2. So our final answer here is going to be y equals 1/2 sine 2x plus 5/2 for the interval of negative infinity to infinity, because the sine function has no inherent discontinuities to it. So there are no restrictions on our domain here. All right, for our next one, we've got dr dt is 1 over t minus 2 plus 1 over t. So once again, we're just going to integrate here, giving us r is equal to, well, 1 over t minus 2. That's another simple u sub. It's just natural log absolute value t minus 2. And then we also have natural log absolute value t. And of course, plus our constant. So what we can do is we can plug in our t value of 1 and our r value of 5 to solve for the constant. So we have the natural log of the absolute value of -1 plus the natural log of 1 plus our constant. Well, that just gives us, since the natural log of 1 is 0, both of these evaluate to 0, and we get a constant of 5. So r is equal to the natural log of the absolute value of t minus 2 plus the natural log of the absolute value of t plus 5. But now we need to start being careful about our interval of validity. And if we look at this, we know that we cannot take the natural log of negatives, which isn't going to be a problem here because both of our natural logs have absolute values on them. But we also can't take the natural log of 0, which means that the things inside cannot equal 0. Right, so t minus 2 can't be 0. In other words, t can't be 2. And also, t cannot be 0 for the natural log absolute value t portion. So we have discontinuities at both 0 and 2. And so when we look for the interval of validity for our differential equations, we can only pick the one continuous piece of the domain of the function that includes our initial condition. So if I have only discontinuities at 0 and 2, right? That's like having negative infinity to 0, 0 to 2, and 2 to infinity. But we're not allowed to put all of those. We can only choose the one that includes t equals 1, which is from 0 to 2. So we'll say for 0 to 2, and that should be our final answer there. All right, for our next one here, in order to integrate this, we're first going to have to rewrite it by dividing both the 5x by the cube root of x and the 2 by the cube root of x. So 5x divided by the cube root of x is just going to be 5x to the 2/3, x to the first divided by x to the 1/3, and then plus 2x to the -1/3. So now when I integrate, right, we'll go up from 5x to the 2/3 to 5/3 and divide by 5/3, which gives us 3x to the 5/3. And then plus over here, 2x to the -1/3 will become 2x to the 2/3. We'll divide by 2/3 or multiply by 3/2. So we get 3x to the 2/3 plus some constant. And we're given that, I shouldn't have put a y here, right? This function is actually, it was dz dx. So this is going to be z is equal to 3x to the 5/3 plus 3x to the 2/3 plus a constant. When x is 1, z is 2. So we'll say 2 is equal to, well, let's see, x to the 5/3. If it's 1, it's just 1 to the 5/3. So we have 3 plus another 3 plus our constant. Or our constant is -4. So our final answer here should be z is equal to 3x to the 5/3 plus 3x to the 2/3 minus 4. And then we have to think about our interval of validity. Well, I have cube roots. You can cube root anything. I don't have square roots where it has to be positive. So we can cube root any number. So there are no restrictions on this. This is just for -infinity to infinity. If we had an even root, then we would need to worry about making the thing positive. All right, we got our next one here. We got dy dx is secant squared x minus x. And that when we plug in 0 for x, we need to get 3 for y. So same process here as all the other ones. We're just going to go ahead and take our integral here. So the integral of secant squared is just going to be tangent. So we're going to have y is equal to tangent x. And then the integral of x is x squared over 2. And we'll have some constant attached to it. So we have y equals tangent x minus x squared over 2 plus a constant. When we plug in 0 for x, we need to get 3 for y. So tangent of 0 is just 0. And 0 squared over 2 is just 0. So we end up with a constant of 3. Well, our final answer should be y equals tangent x minus x squared over 2 plus 3. But we have to think about the interval of validity. The x squared over 2 doesn't cause any issues, nor does the plus 3. But tangent of x does, right? X cannot be pi over 2 plus any pi n, right? Because that's when tangent has asymptotes, vertical asymptotes. And so that means that we're having discontinuities at things like -3 pi over 2. In fact, everything before that, right? And -pi over 2, and pi over 2, and 3 pi over 2, and so on. Right? Well, we need to pick the single continuous piece that includes 0. Well, that's going to be from -pi over 2 to pi over 2. So that will be our interval of validity for this problem. All right, for our next one here. Again, we're just going to integrate this. This one should be a pretty straightforward inverse trig integral. We're going to just get a is equal to 2 inverse tangent of t plus some constant. Or if you prefer, 2 arctangent t plus a constant. When a is pi, t is 1. So we'll say pi is equal to 2 inverse tangent of 1 plus a constant. And of course, there's an infinite number of times when the tangent equals 1, but we want the one that is actually like in our restrictions for inverse tangent, which means the output has to be between -pi over 2 and pi over 2. So that tells us that the inverse tangent of 1 is just going to be pi over 4. So we have pi equals 2 times pi over 4 plus a constant. Well, that's just pi minus pi over 2 to solve for c. So c is pi over 2. And our final answer should be a is 2 inverse tangent t plus pi over 2. And of course, you can take the inverse tangent of any value. And so this is valid for -infinity to infinity. All right, our next one here, we're looking at dy dx is 2x over root 1 minus x to the 4th with an initial condition that when x is 0, y is 3. So we'll start off by doing the integration here. We have to think about the fact that this looks a lot like an inverse sine function. If I let u equal x squared, then du would be 2x dx. And I've got the 2x, which would make this look like 1 minus u squared, right? So really what I'm looking at is an integral of du over root 1 minus u squared, which is just the inverse sine of u. Or in this case, the inverse sine of x squared, plus some constant. And so we'll just find out what that constant is. When x is 0, y is 3. And since the inverse sine of 0 is 0, we just get c equals 3. So our final answer should be y equals the inverse sine of x squared plus 3. And of course, inverse sine of x squared plus 3. We have to think about the interval of validity. We can only take the inverse sine of things that are between -1 and 1. Right? So the inverse sine of anything has, the value that we take the inverse sine of has to be on that interval. So that means that the thing that we're taking the inverse sine of, x squared, has to be less than or equal to 1, greater than or equal to -1. Well, the greater than or equal to -1 part's not an issue. Right? We know that x squared is always going to be more than -1. But to make it less than 1, right, if x squared is less than or equal to 1, that means x has to be between 1 and -1. So that when I square it, I'm still getting something that is less than 1. So our interval of validity here is going to be from -1 to 1. All right, our next one here is our first separable differential equation, which means we need to get all the y's on the left with the dy, and then the dx over to the right-hand side with the x values. So we'll start here with multiplying the y over, giving us y dy is equal to 1 over x dx when I bring the dx over to the right-hand side. We'll integrate both sides, giving us y squared over 2 is equal to natural log absolute value of x plus a constant. And right at this point, we should start thinking about restrictions on the domain. Right? We know that x cannot be 0, so I might make a note of that off to the side. Even if that doesn't still show up in our final result, we have to take that into account because it was a restriction on one piece of it as we went through. So we know that x can't be 0, so we'll make a note there. Now we're going to solve for our constant. So when x is 1, y is supposed to be 2. So 2 squared over 2 is equal to the natural log of 1 plus c. Well, 2 squared over 2 is just 2. And the natural log of 1 is 0, so we get a constant of 2. So we now have y squared over 2 is equal to natural log absolute value of x plus 2. In order to solve for y, we will just multiply by 2 to start with. Y squared equals 2 natural log absolute value of x plus 4. And then we'll square root. When we square root, we get the positive and the negative here. But I need to get a positive value for y. So when I square root, I can't take the negative square root. Like if I had got when y is 1 equals -2, I would be taking the negative square root. But I want the positive square root here. So the square root of 2 natural log absolute value of x plus 4. And now we again have to think about the interval of validity. So we already knew that we had a restriction here that x couldn't be 0. So we'll think about that. But we also have to think about what makes this final result undefined. Well, anything that makes the inside of the square root negative would be a restriction on here. So we need to set that equal to 0. We'll do that over here. 2 natural log absolute value of x plus 4 equal to 0 to see where that cutoff point is. So if we subtract 4 and divide by 2, that gives us natural log absolute value of x equals -2. And if we raise this to the power of, as a power of e, right, we'll end up with e to the natural log absolute value of x equals e to the -2, or absolute value of x is equal to e to the -2. And so we've got x is equal to plus or minus e to the -2 as places where this thing inside the square root changes from positive to negative potentially. And we've got a restriction here on this then. So we know that if I put in something, we'll make a sign chart even actually just to show this. So like if I put in a sign chart here for negative e to the -2 and e to the -2, right? Something between them would be like 0. And if I put in 0 to this, I get a positive value here on my 2. Well, actually, I can't put in a 0 here. Let me put the 0 in here also as a restriction, right? So if I put in something more than e to the -2, like a billion, I get a positive here, right? 2 natural log of a billion plus 4 is clearly positive. And if I put in something between 0 and e to the -2, though, I'm going to end up getting something that is negative. And so since my initial condition here is that I want to be able to plug in 1, right, and get 2, we can see that e to the -2 towards infinity is going to be the appropriate value here, because e to the -2, right, or 1 over e squared is less than 1. And so we need to go towards infinity there to include our value of x equals 1. So we're going to say for e to the -2, and I should put that in a bracket because we can include that, because we are allowed to have a square root of 0. So e to the -2 all the way to infinity. And that should be our final answer there. All right, for our next one, we've got dy dt equals e to the y plus t, and y equals 1 when t is 0. So once again here, we're going to separate the variables. In order to do that, though, we're going to rewrite e to the y plus t as e to the y, e to the t, right, using exponent rules. And now we'll divide by e to the y and multiply by dt, and then integrate. Now the right-hand side here is just e to the t plus our constant. The left-hand side, we can think about that using our u substitution here. Like if we rewrite it as e to the -y dy, right, if we just move that up to the numerator and make the exponent negative, then we can do the substitution where u is -y and du is -1 dy. And so we'll put a negative inside and a negative outside, which gives us -e to the -y as our integral here. So we have -e to the -y is equal to e to the t plus c. When y is 1, t is 0. So we'll have -e to the -1 equals e to the 0, or just 1, plus c, giving us a constant of -1 over e minus 1. And so then we will just go in here and rewrite our -e to the -y is equal to e to the t minus 1 over e minus 1. We'll divide everything by a negative to start with. So that's going to give us e to the -y is equal to 1 plus 1 over e minus e to the t. We just flip all the signs on everything. We'll take the natural log of everything, giving us natural log of 1 plus 1 over e minus e to the t. And then we'll divide by a -1, giving us y equals the opposite of the natural log of 1 plus 1 over e minus e to the t. And so that's great. That's our solution, but we also still need to find the interval on which this thing is valid. And so what we have to do is we have to figure out when is 1 plus 1 over e minus e to the t greater than 0, because we can't take the natural log of things that are less than 0 or even equal to 0. So if we set 1 plus 1 over e minus e to the t greater than 0 and solve for t, right, that'll tell us that e to the t, if we add that over, e to the t is less than 1 plus 1 over e, or that t needs to be less than the natural log of 1 plus 1 over e. And so our interval of validity here is going to be negative infinity to the natural log of 1 plus 1 over e, which is all of the things that are less than the natural log of 1 plus 1 over e, which will include t equals 0 on it. All right, for our next one here, we've just got dy dx equals x e to the x squared minus ln y squared. And when x is 0, y is 1. So we're going to use our exponent rules once again here to just rewrite this as dy dx is equal to x e to the x squared. And then we're going to divide by e to the natural log of y squared, right? Because we have x squared minus ln of y squared in the exponent. So when we have a minus sign there, we can drop it to the denominator as e to the ln of y squared. And we'll continue to rewrite this as dy dx equals x e to the x squared just over y squared. And because e to the ln of y squared is just y squared. And so now we can separate the variables, giving us y squared dy is equal to x e to the x squared dx. We'll integrate both sides, giving us y cubed over 3 plus some constant, which again, we ignore that constant because it can just be flipped over to the other side. So we get y cubed over 3 is equal to, and when we do this x e to the x squared, right, the substitution is u is x squared, du is 2x dx. So we put in the 2 and the 1/2, and it just ends up being 1/2 the integral of e to the u du. So we have 1/2 of e to the x squared plus some constant. And so from there, we'll just solve for our constant. We'll do that over here. When x is 0, y is 1. So if y is 1, the left side is 1/3. And if x is 0, the right-hand side is just 1/2 of e to the 0, or just 1/2 plus a constant. If we subtract, c is negative 1/6. So now we have y cubed over 3 is equal to 1/2 e to the x squared minus 1/6. We'll multiply everything by 3 to get 3/2 e to the x squared minus 3/6, or 1/2. And then we'll just cube root. So we have y equals the cube root of 3/2 e to the x squared minus 1/2. And this doesn't actually have any restrictions on it. You can take any x value and square it, and we can take any number then and do e to that power, multiply by 3/2, subtract a half, and you can cube root anything, positive, negative, or 0. So no restrictions. This is just for negative infinity to infinity. All right, for our next one here, we have sine x, cosine squared y over sine y. So we got quite a bit going on here. But we'll separate the variables. So I'll multiply by sine y and divide by cosine squared y. So we got sine y dy over cosine squared y is equal to sine x cosine x dx. And we just want to integrate both sides. Well, sine y over cosine squared y is actually the same thing as secant y tangent y dy. And then we'll still have the integral of sine x cosine x. If we let u equal sine x, though, du is cosine x dx. And so we just have an integral of u du here. So on the left-hand side, we just end up getting secant y. And on the right-hand side, we get u squared over 2 plus our constant, which is just sine squared x over 2 plus our constant. And then from there, we'll immediately plug in our values to find our constant. So the secant of y, the secant of y, so y is equal to 0. So secant of 0 is just 1. So we have 1 equals the sine squared of pi over 4. Well, the sine of pi over 4 is root 2 over 2, right? So if we square that, we're going to get 2 over 4, right, or 1/2. And so sine squared of x is a half, and then we have 1/2 divided by 2, which will be 1/4 plus our constant. So we have a constant of 3/4. So off the side here, we've now got secant y is sine squared x over 2 plus 3/4, and y is equal to the inverse secant of sine squared x over 2 plus 3/4. And of course, then we have to figure out what our interval here of validity is, right? And so in order to do that, we need to note that we can only take the inverse secant of things that are greater than or equal to 1 or less than or equal to -1, right? So like the inverse secant of x exists only for x greater than or equal to 1 and x less than or equal to -1. Well, we have the inverse secant of something being squared over 2 plus 3/4. So what we've got is a positive value here, which means we don't really need to worry about the x is less than or equal to -1. We just need to figure out when is sine squared x over 2 plus 3/4 greater than or equal to 1. So we'll use a little bit of space over here to figure that out. We want sine squared x over 2 plus 3/4 to be greater than or equal to 1. So we just solve this. We get sine squared x over 2 is greater than or equal to 1/4, or sine squared x is greater than or equal to 1/2. And so if we want to figure out when is sine greater than or equal to 1/2, well, there's a couple of options here. One is either that the sine of x is less than or equal to -1 over root 2, or the sine of x is greater than or equal to +1 over root 2. And so if we're talking about plugging in pi over 4 to this, right, I'm not going to be worrying about negative values over here. I don't really need to worry about negative values because we're plugging in pi over 4. And over here, this is going to tell me that x is going to have to be greater than or equal to pi over 4. Right? And so if I do that, and x is greater than or equal to pi over 4, then, and I guess we should look at this -1 too. Right? This is going to tell me that x is less than or equal to, this will actually be important, -pi over 4. And for each of these, we have like a plus pi in on them. And because at pi over 4, right, we're equal to, we're equal to 1 over root 2 or root 2 over 2. But, because sine repeats, like we have this repetition, because it's a cyclical function, right? A sinusoidal function, it repeats every 2 pi, or it flips back and forth every pi. It flips signs. And so what we've got here then is that our x value needs to be greater than pi over 4, but also, so we're going to put that in here, greater than or equal to pi over 4. So I'll put that here. But, and that's, I'm picking that because that's included in our value here, but also less than or equal to negative pi over 4 plus pi n. Well, negative pi over 4 plus pi is 3 pi over 4. So we're going to have to be between pi over 4 and 3 pi over 4 for this to be valid. That's our cutoff point. All right, just a few more of these here. So this one we got dy dx equals x plus 1 over y, or y dy is equal to x plus 1 dx if I separate the variables. And so if I integrate, we just get y squared over 2 equals x squared over 2 plus x plus some constant. And we'll immediately solve by plugging in 0 for x and negative 2 for y. In other words, we get a constant of 2. So we've got the function now, y squared over 2 equals x squared over 2 plus x plus 2. We'll multiply by 2, giving us y squared equals x squared plus 2x plus 4. And when we square root, we get a positive or a negative x squared plus 2x plus 4 inside the square root. But we know that when I plug in 0, we need to get negative 2, which means I'm not going to choose the positive square root in this case. I'm going to choose the negative square root so that it satisfies my initial condition. We still do need to figure out an interval of validity. We have to make sure that x squared plus 2x plus 4, we have to figure out when is that greater than 0. Well, if you just try to solve that to see if it has any x-intercepts, you'll see that if you do the discriminant, b squared minus 4ac, you end up with 4 minus 16, which is negative, which tells us that this quadratic never equals 0, and it's concave up. So if it's never equal to 0 and it's concave up, opens upward, we know that there's no restrictions on it. It's never going to equal 0, which means that this square root can never be of a negative value. So our interval of validity is going to be negative infinity to infinity. All right, another one here. We've got dy dx equals y plus 3 over x minus 2. So this time when we separate the variables, we got dy over y plus 3 equals dx over x minus 2. We'll integrate both sides to get natural log absolute value y plus 3 is equal to natural log absolute value of x minus 2 plus some constant. When y is 1, x is 3. So we have the natural log of 4 equals the natural log of 1 plus c, or c is just ln 4 because the natural log of 1 is 0. And we'll note right off the bat that x cannot be 2. That's going to be a restriction here on our final interval of validity. So as we plug this back in, we've now got natural log absolute value y plus 3 is natural log absolute value x minus 2 plus ln of 4. Well, we'll exponentiate both sides. So we have absolute value y plus 3 is equal to e to the natural log absolute value x minus 2 plus natural log 4, which can really just be written using exponent rules as e to the ln x minus 2, absolute value x minus 2, times e to the ln 4. Or we can just rewrite it as 4, because e to the ln of 4 is 4, and absolute value of x minus 2, because e to the natural log absolute value of x minus 2 is just absolute value of x minus 2. When we clear off the absolute value, we get plus or minus 4 times the absolute value of x minus 2. We want to pick whichever one will make our initial condition true. So if we plug in 3 for x there, right, we get 4 times 1. So we either have positive or negative 4 is equal to 1 plus 3. Well, that's clearly the positive version there. So I don't want the negative, I want the positive. And I don't really need to put a plus sign in front. We'll just leave it as 4, absolute value, x minus 2. And then we'll subtract 3. So y equals negative 3 plus 4, absolute value, x minus 2. Our only restriction on the domain was that x couldn't be 2, we noted from this natural log we had. And so we need to pick the interval that includes 3. Well, that'll be from 2 to infinity, right? Because there are no other restrictions. So we would normally have a domain from negative infinity to 2, 2 to infinity, but we only pick the single continuous piece that includes x equals 3. All right, here is our last one. And so let's start by separating the variables here. We've got y minus 2 dy equals x squared minus 1 dx. We'll integrate both sides to get y squared over 2 minus 2y is equal to x cubed over 3 minus x plus some constant. We'll plug in our initial conditions that when y is negative 4, x is 3. So if y is negative 4, we have negative 4 squared, which is 16. And 16 over 2 is 8. And then minus 2 times negative 4 will be plus 8. And then when we plug in our 3, we get 3 cubed is 27. 27 divided by 3 is 9. So we have 9 minus our 3 plus c. For 16 equals 6 plus c, giving us c is equal to 10. So this can now be rewritten as y squared over 2 minus 2y equals x cubed over 3 minus x plus 10. And in order to solve this, first let's first multiply by 2 just to get rid of that y squared over 2. So if I do that, we'll have y squared minus 4y equals 2/3 x cubed minus 2x plus 20. And the reason I'm going to do that is so that I can solve for y really easily by completing the square. So completing the square says take the b value, right, negative 4, right here on the negative 4y, and divide that by 2. So negative 4 divided by 2 is negative 2. And then square the negative 2, which is 4, and add that to both sides. So I'm just going to say y squared minus 4y plus 4 is 2/3 x cubed minus 2x plus 24. Now I can rewrite the left as just y minus 2 squared, leaving everything else the same. And then I can square root both sides, giving me y minus 2 equals plus or minus the square root of 2/3 x cubed minus 2x plus 24. And then our final answer here is just going to be y equals 2 plus or minus that. So we'll put that on a new page here. We'll run out of room. We got y equals 2 plus or minus the square root of 2/3 x cubed minus 2x plus 24. Remembering that our initial condition, right, our initial condition was that when x is 3, y is negative 4. So I need to get negative 4 is 2 plus or minus the square root of, well, when I plug in 3 here, that becomes 18 minus 6 plus 24. And if we plug in 3 for x, we have 27 over 3 is 9, times 2 is 18, and then minus 6 plus 24. So we end up with negative 4 equals 2 plus or minus the square root of 36. Well, to get negative 4 from a 2 plus or minus 6, I need to choose the minus, right? Negative 4 is 2 minus 6. So my final answer is going to be 2 minus the square root of 2/3 x cubed minus 2x plus 24. And I know it asks for the interval of validity on all of these. This particular one, solving 2/3 x cubed minus 2x plus 24 is, unless you know the cubic formula, not going to be solved without a calculator. And so I'm not going to bother worrying about the interval of validity for this one. On the test, there won't be any where the interval of validity isn't able to be solved algebraically without a calculator. So don't stress about the interval for this one, even though I did, on the answer key, I'm sure I did put the actual interval. Don't worry about it for the test. You won't ever have to use a calculator to find the interval of validity on the test. And that is the end of our differential equations test review walkthrough. You should be ready for all of the parts of the test that are not specifically AP style FRQs.